Okay, so there's this concern that people seem to have when you're doing work problems. They get so hung up on work being force times displacement times cosine of theta. And that really is what work is defined as when we're talking about it at the beginning of this course. But one of the things that we also notice is that work could be described as the change in the amount of energy that something has, because work is the process of giving energy to something or taking energy from something, but by applying a force to something across a distance. And so I don't want to get rid of this whole idea of force across a distance, but there becomes an issue when the work that's being done is done by a force that changes as the thing moves. Okay, so I want to give you a really nice example of that when it comes to like large scale things. If I have a planet, we just talked about planets, but if I have a planet and there's a rocket ship that blasts off from this planet, you can imagine that this rocket ship, and I know it's not the best of rocket ships, but between when it's at this point and this point, you know that the engines will have had to have done some work. In other words, they will have had to have forced this rocket to move by a certain distance. Especially if it's going at a constant pace, at a constant speed, you would probably even recognize that the force that it would have to apply at the beginning would be different than the force it would have to apply at the end if it's going to keep a constant pace, right? So people say, okay, so force is applied, but because as you get further from a mass like a planet, the gravitational force diminishes since the R values get bigger. According to that old equation, Fg equals G m1 m2 over r squared, the actual force that you're overcoming gets less and less and less and less and less, so that F value is going to change as the displacement varies, okay? And people sometimes will draw little graphs where, oh, the force that you're applying drops off as some inverse square law. You've seen that graph before? The force that you're feeling as you get further and further away from a planet actually drops off as you get further from a planet. So that's the way the force graph might look. That's a tricky thing to deal with, except when you remember that work is the change in energy that you've either given to something or taken away from something. Because although it's going to be hard to calculate force times displacement where force varies, what I can do is calculate what EG is at this position and what EG is at this position. Let's call it positions A and B. And I could calculate EGA by using G m1, m2, where mass 1 and 2 are the rocket and the planet, divided by RA, which is the distance the rocket is when it starts this little trip. The distance between the rocket and the center of the planet, that is. And you could calculate this gravitational potential energy for when the rocket's at its second position. And by finding the difference between those two, that is, work equals EGB, which is the final gravitational potential energy, minus EGA, the initial gravitational potential energy, that change in energy would be the amount of work that I'd done. Now, I don't want to labor this by putting actual numerical values onto it, but you definitely could figure out how much work a rocket engine does as the spaceship blasts off and travels from one planet, or travels away from a planet. And I forgot the negative signs. I'm sorry. There should be negative signs in front of those gravitational potential energies. Some people say, why are the negative signs there? Well, I mean, there is a reason in terms of dot products that you might argue that are for why they're there, but it also works out in terms of the math. Check out at position B. At position B, tell me about that R value. Is it really big or really small? Yeah, really big, which means that at position B, you're going to have, what? Is this going to be a large value or a small value? Yeah, so it'll be a tiny value, but a tiny negative value. And a tiny negative value minus a big negative value is a tiny negative value plus a big positive value, which means that the amount of work that you've done would be a positive value. So mathematically, it may work out that way. But then there are other people that say, hey, wait a minute, what happens in the limit scenario? What about what happens to this R value when R goes to infinity? What does happen? What becomes gravitational? What becomes the value of the gravitational potential energy at the infinity limit for R? Yeah. In the limit where r becomes infinity, Eg becomes 0. Thank you. And then conversely, when Eg approaches 0, what's the r, or approaches infinity rather, what's the r value got to be? 0, yeah. So way back here, if I ever can get to the center of my planet, you would say that I have infinite gravitational potential energy. Well, that can be a little bit confusing, but mathematically it works out. Not something we need to be too concerned about. All we're saying is that the magnitude of your gravitational potential energy is big when you're close, and it's small when you're far away. But for the most part, all we really care about is what's the difference between your gravitational potential energy when you're close and when you're far away, because that's how much work you would have to do to get to that different distance, or how much energy you would get out of it if it fell from that far distance to a closer distance. And we dealt with that with falling objects, with somebody that's 20,000 meters up from our planet previously. In the end, though, E total is still going to be the sum of the EKs that the rocket might have, the EG that the rocket might have, and any other energies that rocket might have. Oh well.